Okay. Okay. So, Namaskar, Shubho Sondha Sabaike. Good evening, everyone, and a warm welcome to Kolkata R User Group's meetup, rather virtual meetup. So, after a short break, we are again back with another new session. So, I am Somrit, a lead organizer of Kolkata R User Group, and by profession, senior statistical modeler and art developer. So our group is proud to be a diverse and inclusive community, welcoming individuals from all backgrounds and industries. So whether you are a student, researcher, or professional, or simple curious about statistics, data science, and art, we invite you to join our session, ask questions, and learn from each other. And if you missed out our previous sessions, do check out our YouTube channel. The recordings are available there. And do not forget to subscribe the YouTube channel and do follow us on LinkedIn to get all updates. So without further ado, let's welcome today's distinguished speaker, Dr. Ayan Paul, who will enlighten us on the topic navigating model selection and regularization, a journey through the corridors of art. So Dr. Ayan Pal is an assistant professor in mathematics at Institute of Engineering and Management, Kolkata. So let's welcome Dr. Ayan Pal and over to you, Mr. Ayan Pal.
Thank you very much, Somrit, for this nice introduction. And I'm really grateful for giving me such opportunity to present myself uh, in front of your participant. This is really a great opportunity. So without any further delay, let us start today's session. Okay. So I will switch today's session in between PowerPoint presentation and the art software, so that all of you can correlate what I am going to present or what I am going to deliver to you. Okay. So let us start. So can I share the screen? Have you given me the permission?
Yes, let me stop sharing and let me give you the permission.
Okay.
Yeah, so try to share your screen.
Yes, I think
Yes, it's visible. Yeah.
it's visible. Am I audible clearly, right?
Yes, yes, you are audible.
So I have given the full screen mode. So is it visible, the full screen mode?
Yes, it is visible properly.
Okay, okay. So I'm starting my presentation. So first, let me select the pointer. Yes, okay. So as per the title that I have given for this talk, today's talk, that is navigating model selection regularization. So today's talk, I have bifurcated today's talk into two portions. The first portion is a very basic and fundamental thing. And for the second portion, I will jump to the model selection. But before jumping into the model selection process, we need to understand why model selection is too much important in today's world. Because generally, when we are dealing with any kind of data set, we are just collecting the data set and we will store the data set in the Excel file, and then we will import the data set in corresponding softwares, whether it may be R, maybe Python, maybe Stata, maybe MOS, and we will perform a couple of analyses. But we don't know why the model selection is actually required for this thing. So I will put some light on this thing on the very first portion of my talk. And then after that, I will jump to the very specific, or you can say some specific methods of the model selection. So with this short introduction, let me start my presentation. Okay. So if you have any questions, you can immediately stop me during my talk. I'll be more happy. And then you can ask me before raising your confusions. Okay. Achha, okay. So the title of this slide is Fundamentals of Data Science. So whenever whenever we will receive any kind of data set, generally what we can do, we generally bifurcate or we partition the data sets into two zones. The first one is the training data, and second one is the testing data. But the question is, after receiving this data set or after partitioning into training data or testing data, what we are performed or what we will perform. Now, with the help of the training data, we generally fit different kind of models on the training data. And we will choose any one of the model from the training data based on the performance of the data set on that specific model. And after selecting the model, we use the testing data for the prediction purpose. So that's one process. Generally, we are adapted or we are habituated with this type of process. But sometimes it is really tough for us to segregate the data set into training data or testing data. So then, generally, what we will do, we will collect the data set and then we will fit the models by assuming that the training data and the testing data will give the similar type of accuracy. That's why I am pointing this specific thing, that is feed the models by assuming that the prediction accuracy for both the train and test data are almost identical. This is the general trend I have find in each and every student or many of the researchers. In fact, when we review any kind of papers, research articles, we have also find this thing. But I am quite astonished to see that. Yes, this is the procedure. I am not saying that this is not wrong. This is the wrong process. No, this is not the wrong process. This is obviously right process. But before applying this type of process, we have to understand the underlying mechanism or underlying theory in data science. So that's why the term has been coined data science. That means what science has been hiding or what science has been hidden under the data set. Okay. So that's why the major concern is, are we on the right track? Yes. So are we on the right track? It's- Presentation is visible. Oh, what happened?
Yes, it is visible.
Presentation is visible.
Yes, yes. Yeah, we can see your screen.
Acha, okay, okay. So I don't know what happened to my screen. So that's why I'm asking. Okay. So
Hmm.
yes. My concern is, are we on the right track? That means we will collect the data set, we will import the data set from Excel file to our corresponding softwares, and we are just assuming that training and testing data are performing the same manner. So that's why I'm asking the question: are we on the right track, or are we guessing the same thing, right thing? So my first portion of my of today's talk is totally devoted on that portion. Okay. So let me move into the second slide. So that's why I will use some simulation on the R software first by collecting the data set from a specific function. Okay. So that all of you can correlate what is happening in between the training data set and what is happening in between the testing data set. That means what is the correlation between testing and training data set. So since this entire session is devoted on the R software. So that's why I have prepared my the codes in the R software or R studio rather. I can say, and you can also prepare this session or you can also prepare these codes in any of the softwares. But the essence must be same, or the logic must be same. Okay. So first I have simulated the specific observation data set that is displayed in the right panel of my slide from this specific function sin pi x. Okay. So for the sake of simplicity or for just sake of today's session, you will just consider this data set as the observation. That means you have collected the data set from any experiment or from any field. Okay. So yes. So the number of predictors is present in the x-axis and the number of observations is present in the y-axis. And you can see that the pattern of the data set is showing some wavy structure. That means as I have collected the data set from the sine function, so it is quite obvious that the sine function has some periodic nature. So the data set is also showing some periodic characteristics. Okay. So as I have mentioned, after collecting the data set, either we will partition the data set into training and testing data set, or we will assume the whole data set as a training data set, and then we will perform the rest of the operation. So in this sense, this is one kind of simulation experiment. So you can partition the entire data set into two portions. That means training and testing. So my next slide will demonstrate that how can we partition a data set in our software into training and testing. Okay. I'm not going to explain this data set in the R software because this code is very much elementary, and if I will share this material to you, you can run the code in R software and you will definitely get the same output that is displayed here. The point is I am trying to pass on the message regarding the correlation between training data and the testing data. The mistake that is occurred mostly during the data filtration or the data simulation process. Okay. So see the partitioning of the data set. So as I have mentioned, I am splitting the entire data set that you have seen in my last slide into two portions, training and testing data. By considering that 70% of the data is going into the training zone and the rest of the portion, that means the 30% of the data will going in the testing zone. Okay. So you can choose this specific ratio according to your choice. You may choose 60-40. That means 60% will going into the training zone and 40% may go to the testing zone. That is your choice. But generally 60-40 or 70-30 is generally observed. But please do not put the ratio of the training data below 50 or below 60 because 50-50 is acceptable. But beyond 40-60, that means 40% is going to the training zone and 60% is going to the testing zone, that is generally not acceptable. Because since we are dealing with the machine learning, that means we are training the machine with the help of the data set, and we all know if we input or if we provide more data set to a specific model, our accuracy of the model will increase. So that's why it is very much important to put the training data with the more observations. Okay. So that's why we put the 70% into the training zone and 30% into the testing zone. We have partitioned the data in this manner. Okay. So after partitioning the data, we have raised some key questions. I believe the questions that I will display here, after that, no questions will be there regarding the training and testing participation or regarding the analysis. Sorry, anyone here interested to? Achha, okay, that's a different issue. Okay. Okay. So, what are the key questions? So, I will display the first question. Yes. So, as I have mentioned, that most of them are thinking that training and testing data are predicting or are behaving in the same way. That means whether the accuracy level of the training and testing data are same, that means the accuracy that is given by the training data and the accuracy that is given by the testing data, are they significantly identical? That means the inference that is drawn by the testing data and the inference that is drawn by the testing data, are the accuracy are same? Are the accuracy same for both the data sets? So that's my first point, and that is the main important point of this talk. Okay, and the second one, if the accuracy level of the training data and the testing data are same. So suppose for the sake of simplicity, we are considering that the accuracy level of the training data and the accuracy level of the testing data. One second. Yes. So the accuracy level of the training data and the accuracy level of the testing data, for the sake of simplicity, we are assuming these are same. But if these accuracy levels are same, then is it possible or do they propagate any kind of error during the fitting process? That means when we are going to fit or we are going to perform any kind of regression work, do this partition or do the misconception of this same accuracy level propagate any kind of error or produce any kind of error during the regression process or during the regression work? So that's my second question. And the third question is, yes, we all know that when we are collecting the data or when we are performing any kind of regression work, we are generally deal with couple of predictors, couple of variables. 3 variables, 4 variables, 5 variables, 7 variables, 10 variables. Maybe it may be for the large data set, maybe 100, 200 variables. So will the accuracy level of the training data and testing data depend on the model flexibility? That means the number of model parameters or number of model predictors. That means suppose a data set contain 100 model parameters or 100 predictors or 100 variables, will the training data behave in a similar fashion for the 100 data set, or will the testing data behave similar fashion for the 100 variables, or will there be some discrepancy in between the testing data or training data for the 100 variables or 100 predictors? So I believe these are the three important questions before the important question for analyzing the training and the testing data. Okay, so I will let you know all of these questions, or I will give some information. I will put some light on these questions in my next couple of slides. Okay, so up to that, I have collected the data set and I have just partitioned my data set into training and testing. I haven't performed any kind of statistical analysis up to this portion. Just collected the data set and then I have just partitioned my data set into training and testing. Okay. Okay. I am jumping to my next slide. Okay. So measurement of accuracy. So as I have mentioned or I have told a couple of times regarding the accuracy level or the accuracy between the training or accuracy of prediction of the training and testing data. My point is, or my questions is, how can we measure accuracy from the very, very ground level? Yes, I know couple of statistical metrics or couple of statistical objects is there for measuring the accuracy. But what is the very, very basic measurement of accuracy in the prediction process? I will put the light on that. That is nothing but the mean square error. The participants are present here. I believe it is very much useful tool, or you will know about the utility of the mean square error or the MSE. Okay. So mean square error is nothing but the difference between the observations, as I have mentioned here, observations and the prediction. That means the observations we have collected and the prediction we have drawn through the regression work, the squared difference or the squared average difference of this specific thing is known as the mean square error. So again, my point is whether the mean square error of the training data and the mean square error of the testing data are at par with each other. That means whether the trend of the mean square error or whether the trend of the testing data are behaving in the similar fashion. If we increase the number of model predictors or if we increase the number of model parameters, That means if we suppose if we consider two model parameters, or if we consider the five model parameters, what will happen in case of the training error, or what will happen in case of the testing error? So that's my point. So that's why I am repeatedly uttering this specific thing regarding the training and testing data, so that all of you can easily understand that what I am going to show you, or what is the actual thing that is presented here. Okay. Okay, so after partitioning my data set from the coding point of view, what I have performed, now I have now I will evaluate the statistical analysis of the training and the testing data. So suppose I am considering that observations that I have shown to you, I am going to regress that observation with respect to the polynomials. Polynomials means, suppose 1 degree polynomial is nothing but the straight line. Or you all know the equations of straight line is y equal to a plus bx. So the power of x is 1. So that's why it is 1 degree polynomial. So if the power of x will increase, then the polynomial will stand into some nonlinear portion. That means they will show some curvy structure. So here I have considered that the maximum degree of the polynomial is 13. That means, so for the straight line y equal to a plus bx, what are the number of parameters? 2, a and b. A is the intercept and b is one model parameter. So if we go for the second degree polynomial, then y equal to a plus bx plus cx square. Again, a is the intercept, b and c are the model parameters. So here maximum degree is 13. That means the polynomial will be demonstrated through the structure y equal to, suppose, a0 plus a1x plus a2x plus a2x squared plus a3x cube dot up to, suppose, a14 x to the power 13. So we will regress, or we will fit from 1 degree polynomial to 13 degree polynomial to both the training and the testing dataset. And then we will check whether any kind of distinct patterns are shown with respect to the mean squared error or not. Okay, so that is actually demonstrated through this R code. Okay, so I am moving to my next slide. Yes, understanding between the train and the test MAC. That's a very much important thing. That is, what is the, again, I am uttering the same thing. What is the correlation between the training and the testing test MAC? Yes. So if we draw the curve, so previously from this slide, you can easily understand that we have evaluated the training MAC and we have evaluated every model parameter. That means, suppose for one model parameter, or for two model parameter, we have collected the information on the training MAC and we have stored under the vector training MAC. And similarly, for the two model parameters, we have collected the information by the test MAC and we have stored the information under the test MAC. And after collecting the information, both the training MAC and the test MAC are nothing but it is converted into one kind of one-dimensional array structure. And this one-dimensional array I have plotted in my next slide. That you are going to see here. Okay. So look at this graph. So this is very, very much interesting, and this is very, very much important from the data science context. Okay. So in the y-axis, I have mentioned that in the y-axis, I have written the mean squared error. Okay. And in the x-axis, I have mentioned the model flexibility. That means the model parameters, number of parameters. So as I have mentioned that I have considered a polynomial up to degree 13. So it is expected that for 1 degree polynomial, two model parameters is there, intercept A and the straight line, and the B paramodal parameter. So for the 13-degree polynomial, so similarly for the 13-degree polynomial, 13 or 14 number of parameters will be there. Okay. So if we increase the number of model parameters, what trend is showing by this picture, I will let you know, or I will let you explain. So first we'll concentrate on the training MAC. Okay, that means training MAC means the mean square error that is received by those 70% of observation. So if you remember, I have partitioned the data set into 70-30, 70% for the training and 30% for the testing data set. So see, the mean square error that is displayed by the 70% of MEC is characterized by this specific curve, that is gray curve. Hope all of you can see this specific structure. And for the 30% data set, that is 30% data testing data set, the MEC's characteristics is displaying by the red curve. I will let you know about the irreducible error. I am not currently interested to explain this irreducible error to you because it will distract you from the main context. Okay, I will let you know obviously. Okay, so see, as the number of model parameters is increased, the training MSC is going to decline. Okay, so that's the first point. So as the number of model flexibilities increases, the training MAC declines. So that's a very important point. Why? Because we generally think that if we increase the model parameters, or if we put model parameters more and more, our prediction may be accurate. Okay, our prediction may be accurate, but it may not be true for each and every cases. Why? That is going to be explained by the testing portion. See, so for the testing cases, initially see the MAC or the mean square error is showing the decline pattern or the decreasing trend. That means with the increasing of the model parameters, the testing MAC is declining. But after certain threshold, it is starting in it has been started climbing. Okay, that means it is showing the increasing character, but it is not expected, right? Because what is the general thinking of us? If we put more and more model parameters, or if we consider more and more predictors, or if we collect more and more variables, and if we input more and more variables, maybe our prediction is always true, or maybe we will predict very ideally. But that's not the thing. That's not the thing. So that is the most important thing I have to that is the most important thing I am passing. I wish to pass this message to you. So what is that? So if we increase the model parameters, the test MAC is going to increase in case of decreasing. So what is the ideal case? If we choose the correct underlying model or the correct model, then the mean square error is going to decrease. But the picture is showing some different story. That means if we increase the model parameters, it is not true that the test MAC or the MAC will always going to show the decreasing pattern. So that's why the context of model selection comes into the picture. Because if the training and test MAC will show the same decreasing fashion, for increasing the model parameters, then there is no need of the specific module or the specific chapter model selection. Because because it will then show that by incorporating more and more model parameters, the mean square error is converging or is lying the neighborhood of the zero. Then it is not needed. But this picture actually raise the main or show a alarming symbol that no, we have to think about the model selection process, because the training and testing MSc are showing some different pattern. So that's are the key observations that I have documented here, that with increasing the model flexibility, the training MSc exhibits a consistently declining trajectory that I have mentioned. But the trend may not be necessarily true or may not be necessarily hold for the test MAC, as I have mentioned. why it is happening, that's the underlying mathematics. But due to this time crunch or this, I think this is not the right platform to discuss all the underlying hidden mathematics here. But I will, my objective is to pass on the message that after this presentation or after this talk, when you will analyze any kind of statistical, any kind of data set, then you should keep in mind that the training and testing accuracy of the training and testing data are not same. They are not behaving in the similar fashion. Rather, for incorporating model parameters, you will see that the training data may show some declining pattern, but the testing data are not. Okay. So that's why you can see that testing MSC or the test MSC will show this U-shaped pattern. Always, that means it will first decrease, then after a specific threshold, it will going to increase. So that's the general trend, or that's the standard pattern. The test MSC will always show the U-shaped pattern. That's why as model flexibility increases beyond a threshold, a substantial divergence between the training and test MSC becomes evident. Because you can see that if the training and test MSC are showing the same pattern, then they will converge or they will meet at certain portion. But due to the inherent characteristics of the dataset, the test and the training MSC are not going to show the same fashion. Rather, they will show some divergent character. That means they are diverging from each other. Okay. So as I have mentioned, so now we have to think about the model selection process. Okay. So what is the first step of the model selection? So my next slide will demonstrate this specific portion. That's what is the first step of the model selection process by observing this trait of the train and the test MSC. Okay. See, so you can see this specific picture here where I have documented some important thing. What is that? First, I will display that. Yes, by displaying this table, you can easily understand. See, so when the training and test MAC, both the train and test MAC are quite high, okay, are quite high, this phenomenon is known as the underfitting. That means you are underestimate or your model, rather your model is underestimating your data set. That's why the training and testing data are, the training and the MSC for the training and testing data are too high. And you can see in this case, the model parameters are quite low. That means when the model parameters are quite low, then your fitting is not at all producing a good inference. That's my point. That means too much, that means too much low fixed model, that means consideration of too low model parameters is not a good thing. So that's why I have written here too low model flexibility is not a good thing at all. Okay. So coming to this next portion, overfitting issue. Okay. So you can see a large gap is there for the training and testing MSC if we consider more number of model parameters. That means if we consider more and more number of predictors, that is also not a good symbol because it will produce a large, huge gap in between the training and testing MSC or training or the accuracy of the training and testing data. So that's why this phenomenon is known as the overfitting. That means when the training MSC is low, but the testing MSC is high, that phenomenon is known as the overfitting. So we have to take care of this thing also. So that's why again high model flexibility is not a good thing. That's why I have written this message here that when you are going to fit the model, huge number of model para incorporation is not a good thing. Okay, so that's why we have to always look on the moderate level of model parameter consideration of the model consideration of the uh, moderate level of model parameters. So that's why I have written here, when your training MAC is low, that is not very close to zero, and your test MAC is also very low, that phenomena is known as the good fitting. So that is producing a very good inference to your good inference about your data sets. So that is known as the good fitting process. And for the good fitting, we have to always consider a low level of model parameters. Okay. But my point is, when we collect the data, how can we understand this thing? Because uh, because sometimes, as I have mentioned, we have collect with the data set, the sample size of the data set is too low. So then it will be hard to segregate the data set into train and test portion. Okay. Or similarly, if we receive a large amount of data set also, some experiment, it will also very hard to partition the data set into train and the testing portion. So that's why a specific method is there. Actually, two specific method is there. I will let you show this through slide. The prediction of the testing error with respect to the training error. That means if we consider a data set, the whole data set as a training data set, then how can we predict the test error so that the optimal number of model parameters will be included in our regression work, and so that it will produce a very good inferences. So that's my point. Okay, so that is the main point I will going to show you. That is the entire thing about the model selection process with from the perspective of the training or the testing MAC. Okay, so if you have any questions, you can immediately stop me and immediately ask me. Okay, so that will be better for you. I will be happy to answer each and every questions of you. Okay. So now I am moving to my next portion of the talk, that is the model selection process. Okay. Yes. So this is the some outline of the model selection. So what is the general structure of the linear regression model? So as I have mentioned, so this is Y is nothing but the response variable. That means the response we are receiving with respect to the predictors, and x1, x2, x3. So these are the set of the predictors or the variables that you are collecting. Suppose, as for example, with respect to what can I say? With respect to the grade of any student, what is expected, that the grade will depend on their marks of, suppose, final semester examination, mid semester examination, these things. So the final marks of the final semester examination. Yes. How did you calculate the irreducible error? Very good question. So the actually irreducible error is nothing but the error that is associated with the our samples. Okay. So that is not in our hand, because when we are collecting our errors, when we are collecting the samples from our field or from the experiment, the errors that is happening is not in our hand. So that is nothing but the irreducible error. That means the variance associated with any sample is known as the irreducible error. And as you have mentioned the question, you can see that that is one of the important things. That's the test MAC. The test MAC will always lies above the irreducible error. That means the test MAC will always lie above the mean square error. Okay. Will lie always above the error associated with the sample observation. So that is one of the key and very important characteristics. Okay, hope uh, I am answering you quite well. Okay, so now I am going to my next slide. Yes, what I have mentioned you, that is the outline of the model selection, that is the linear regression cases. So this is the very general structure of the linear regression model. Okay, so where x1, x2, x3, xp are the nothing but the set of predictors of the explanatory, or it is known generally by explanatory variables, and y is the response variable. And how can we execute this multiple linear regression model in our software? With the help of very simple command, that is a LM. LM is nothing but the abbreviation of the linear model. And then we have to put the response data, that means the Y data, and then we will add the predictors as per our choice. Then we have to write the corresponding data file. I will show each and everything by the R software. Okay. Yes. So as you have seen on the last slides, that is, if we increase more and more per model parameters, that is not a good symbol, because in that case, there is a certain disparity in between the training and the testing data. So that's why my first question, are all predictors necessary to explain the linear systems? That means, is it necessary to incorporate each and every model parameters to our regression work? That actually generates the brainchild of the regression or the model selection problem. Okay, so that means, what is the objective of the model selection? So you can see model selection is nothing but a filter, nothing but a filter. So you will put all the predictors in the filter, and it will give the output for some selected or some specific predictors based on its statistical performance. So that's the model selections. Okay. So why the model selection is needed? So you can see that, as I have mentioned, that inclusion of more and more variables, or you can say inclusion of the irrelevant variables, actually generates the complexity of the model structure. So, okay, thank you very much. Thank you. Yes. So inclusion of more and more variables actually unnecessarily populate your model. So it will makes more and more complex to your model. So that is not a good thing. So that's why two agenda is there behind the model selection. The first one is the prediction accuracy. That means that means the accuracy or the mean square error, as I have mentioned, but I will use couple of another metrics regarding the accuracy level. So the accuracy producing by both the training and testing data, or the accuracy level that is producing by the observations, is are same, or is it good with respect to the number of observations and number of predictors? So that's why I have written here, this strategy deals with the number of observations and the number of predictors. Okay. So if n greater than p, that means if you have large number of observations with respect to the predictors, then we can go with all the predictors because your observation is quite large. Okay, but if predictor is too low, that means suppose you have thousands of observations and you have 10 predictors, or you have 20 predictors, then we can go with all the predictors. But if we have the large number of predictors, or if we have more number of predictors rather than the observations or rather than the samples, suppose you have 20 number of predictors, but we have suppose 30 observations, or we have 10 observations, then we have to go to the model selection process. That means then we have to filtering the number of variables or number of predictors. Okay, so suppose we have the 20 predictors and we have the 40 observation. In that case also, we have to go for the model selection process, because the 20-40 ratio is not too high. But if we have thousands observations, but we have 500 observations, that means 500 data set, but we have only 20 predictors, then we can go with all the predictors. But if we have 40 observations, if we have 20 observations, but if we have 40 observations and we have 20 number of predictors, we have to go for the model selection. And as I have mentioned couple of times, that the model interpretability, that is, if we perform model selection in a very good manner, then we can infer, we can produce very good prediction regarding our system or regarding our underlying process. So that's the message I have to pass on through this slide. Okay. So now coming to the segregation or the partition of the model selection process. So actually model selection process can be partitioned into three distinct methods. Okay. So first, the subset selection. So what is subset? So subset is nothing but a portion of any set. Okay. So suppose we have 10 number of predictors as I have mentioned, or we have 20 number of predictors. So what model selection does? They will produce or they will generally filter the number of predictors. That means they will collect smaller number of predictors from the whole set. So that is the subset selection. Okay. That means among large number of predictors, they will collect only couple of parameters or couple of parameters that is relevant to our model. So in that case, two important method is there. You have already heard, believe you have heard the name of this specific thing, that is the stepwise forward regression and stepwise backward regression. Apart from that, one method is there, one basic method is here, that is the best subset selection. There has some distinction in between the best subset selection and the forward regression and the backward regression. I will definitely let you know. Okay. And the second method is the shrinkage method. So what is that? Sometimes, based on the characteristics of the data set, it is not possible to filter the data set with respect to this specific method subset selection. Okay. So sometimes it is needed to perform the shrinkage method. That means the objective of this method is that they will they will estimate, or they will put, or they will shrink the parameter estimates of some model parameters towards zero, or they will produce some zero estimates of the model parameters based on this specific shrinkage method. That means their model parameters are shrinking, or shrunk towards zero, shrunk to zero. So that's the basic underlying mechanism of the shrinkage method. And the famous shrinkage methods are nothing but the lasso and the ridge regression. Hope you have heard or you are familiar with this specific terminology. Acha. The next step is the dimension reduction technique. The same thing, the same thought, that is like the subset selection and the shrinkage method. That is, suppose I have 10 number of predictors, and after model selection we will get 5 number of predictors. So that means I am reducing the dimension of the predictor space. So the predictor space contains 10 number of predictors. After dimension reduction, I am now collecting the 5 number of predictors. So that is the dimension reduction case. And the famous method is nothing but the principal component analysis. So it is very much popular method and very much familiar method. So for today's talk, I will concentrate on the specific one, subset selection, because if I will tell each and every method, then it will take almost 3 hours lectures. So since this is a very short presentation, or this is a very short talk, so that's why I will put my entire concentration on the very first portion, that is a subset selection. I will explain both the theoretical perspective, and obviously I will perform the hands-on session in the R software in front of you, so that all of you can easily understand that how can we get the flavor of the subset selection process in the R software. Okay. Okay. Yes. So yes, I will start my live demonstration through the R software. Okay. So before that, I will let you know about the data set that I am going to consider. Okay. Then I will show you the live demonstration through R software. Yes. So this is the data set. Actually, this data set is nothing but the related to some physiochemical parameters of a molluscan species, because since I am working on the I am working on some data science project, or I am working on some data science research, I am data science work. So that's why this is the data set is also related to some of my research work that I have communicated to a journal. So that's why I have thought that this is the best way to show you, because with the help of a real data, rather the data set that is stored under the R library functions. Because when we have collected the real data, we will face couple of problems. Okay. So that's why it is very much essential to show the demonstration with the help of a very real data set. So now I will switch my presentation to the R studio, as I have mentioned in the beginning of my talk so that all of you can easily understand. Okay, so let me switch to the R's window. So is it visible to each and everyone? Just put a message in the chat box, whether the R portion or the R window is visible to each and everyone or not, or the
Yes,
font
it's
size.
visible, please. It's visible at my end. Thank you.
Okay. So first I will save this file. So all of you know how can we save this file. That is, suppose I am saving it on the desktop folder. Suppose uh, R user. Okay. Oh, yes. Okay. So first we will collect the data. We will input the data. So suppose I am naming my data set the workshop data. Okay. Then I am producing this bit.csv file.choose. Yes. So this is a very standard command to import any data set from the Excel file into the R software. So first we will save the data set into CSV format. All we know how can we save a data set into the CSV format. Then we have to write this specific command file.choose. Then if I execute this line, yes, this will come. So suppose I have stored my data set by mock data selection. So yes, the data set has been now imported into the R software or the R version, R environment. So how can we see the data set? That is, sorry, in R window, that is the to the command of view. Yes. So you can see just beside my present my slide, or you can say my script, a tab is automatically opened by displaying the same data that I have displayed in the my presentation file. Hope you can remember that thing. The same thing, population, ST, SPH, SSL. So all these variables has some specific name that is not, I am not interested to explain the name. Just for the sake of simplicity, assume these are nothing but the variables. Okay. So again, I am switching to my presentation file. Yes. So here, the first portion, that means the population, I am treating this population as the response variable. Okay, so as I have mentioned, that is a Y portion. And the entire variables or the entire model parameters will be treated as the predictors. Okay, so I will treat only the first column as the response variable and the rest of the predictors or rest of the variables as the model parameters or the predictors. So again, I am switching to the R window. Yes. So let's see what is the dimension of the data set. That means how many rows is there, how many columns is there. Yes. So see. So yeah, one question is there, is the font adjustable to your eyes, or I should increase my font size? Please let me know. Is it adjustable to your eyes? Uh, Hope
It's
it is
fine.
here. Oh, sir. Okay. Oh, yes. Yes. Okay. Thank you. Okay. So see in the console portion, what is the output? That is 40 and 25. So that is your data set contains 40 rows and 25 columns. So 25 columns means 25 number of predictors, and 40 rows means 40 individuals is there, or 40 data set is there. Okay. So now I will first perform the multiple linear regression. Okay. Multiple linear regression. So suppose I am just naming the variable name by multiple linear regression. That is equal to, as I have mentioned, LM. Okay. And then we have to write the response variable name, that is pop. We have to put the tilde symbol. And since we are considering all rest of the variables as the predictors, we will put the dot symbol. Okay. Then just I will mention the data, that is workshop data. Okay. So let us execute this line. Yes, it has been executed successfully. So let us look on the summary portion. That is very much important because all we know that the summary in case of R software will produce the basic statistical information. Yes, the summary has been generated. So since it is very hard to you to understand the summary from this short window, so let us again switch to the presentation. Okay. Yes. Yes. So this is the same summary that I have received in my R console. For your for sake of understanding, I have stored this specific thing in the R window. Sorry, in my presentation file. Okay. So here you can see the first column will be the estimate of the model parameters. Okay, the first column will be the estimate of the model parameters. Now the questions is the estimates we have received, whether it is significant at all. That means if we perform 100 experiment, whether we have corrected the experiment 95 times or 99 times or 90 times. So that's actually give you the 5% level of significance, 1% level of significance, 10% level of significance. So you can see 1 star means 0.05. That means 5% level of accuracy. 2 star means 0.01. That means 10% level of accuracy. Okay. That means you have committed only 5 mistake if 1 star is there. If 2 star is there, you have committed only 10 mistake. Okay. So if only 1 star, if only dot is there, that means you have committed 100 mistakes. Okay. That means out of 100, you have committed 100 mistakes. So that is not a very good thing. So see, so in the parameter estimates, in the very last column, so what is that? This represents a p-value, that significance level. Okay. So see, no star is there. That means no parameter is going to be significant. Rather, two parameters are showing 0.1. That means ultimately 10% level of significance. So that is not, 100% level of significance. So that is not a very good thing. Okay, so that is not a very good thing because no parameter is significant. So that is a very bad thing, that no parameters is going to be significant. Okay. So my question is why it is happening that no parameters are displaying the significance level, or the significance level of the parameters are not equal, not a very good are not in the good line. Why it is happening? So in that case, you have to find out the variance associated with the estimates of the model parameters. Because what is happening inside the regression process? Inside the regression process, our software actually regress almost 1,000 lines with respect to your predictors, with respect to data set. For each and every line, they are producing the estimates. Suppose our software has regressed 1,000 times or repeated this process 1,000 times. So they have collected the information of the estimate for 1,000 times. So based on that 1,000 estimates of 1,000 data set, they have produced the variance of these data sets or variance of the estimate. So how can we get the variance of the estimate? The simple command, that is the VCOB. So first I have to store this information under a specific variable. Suppose summary multiple regression. Okay. Yes. So suppose summary dot, yes, multiple regression. So see, so a variance covariance matrix has been given here. It is very hard to understand here. Okay. So generally, the diagonal elements are defining the variance associated with the coefficient estimate. Okay. So that's why I will extract the variance associated with the estimates through the diagonal by collecting the diagonal information that will be collected through this specific command diagonal. So see, so here it is coming again. I am switching my R Studio, my presentation file, so that you can easily understand. Yes. So the variance associated with my coefficient estimates regarding the multiple linear regression. So why I have given these boxes here? Just look at the variance. So generally, what is our intention? Our intention is that our intention is that we will try our best to reduce the variance of the estimates so that our model will show good prediction. Okay, but here you can see the variance is too much high. That is 10 to the power 5. So here the variance is 10 to the power 1. Here is also 10 to the power 1. And here is also 10 to the power 1. And here the variance is 7. Here the variance is 2. That means consideration of all model parameters is not at all a good thing. Okay. So that's why we have to take the consortium of the model selection process to reduce the variance of the model parameters. Okay. So that's why again model selection is very much necessary. Okay, again very much necessary. So again I am switching to my R studio. Yes. So suppose I am starting my process by based subset selection process. Okay. Subset selection. So how can we produce this by subset selection? So a couple of comments is there, but this comment has some fantastic nature. I will let you show why it is fantastic. So this library function has to be installed in your machine. So I have already installed it. So that's why I'm not going to install this furthermore. So leaps. Okay. So suppose the file variable name under which I am performing this thing based subset selection, that is equal to the command name is reg subsets, under which you have to write the response variable pop, then put dot, then you have to mention the dataset name is workshop.data. Then you have to, yes, then you have to specify the number of variables you have to consider. That means you may consider out of 25 5 number of variables for the analysis, or you may consider 10 number of variables for the analysis. But since we are dealing with a real life data set, it will be better to consider all number of predictors, and out of which how much number of predictors will be filtered during the model selection process. That is very much important. So that's why. So since the total number of predictors will be as is 25, so that's why I am just writing number of column with the workshop dot data -1, because we have 25 number of predictors, -1 will give to the 24 number of predictors. Okay. So now I am executing this one, and let's again store the summary information. Suppose base subset dot selection equal to summary of based subset selection. Yes. So summary is coming. So let us see what is the summary. Yes, the summary is displaying here. Again, I will switch to my presentation file for your convenience. Yes. So see. So that's the summary we will receive in the R console. So I will explain the summary because it is very much hard to understand the summary without the explanation. So concentrate on the first row. Okay. So on the first row, under clear only star is there. So that means, so what is the protocol of the base subset selection process? So suppose we have p number of predictors, so we have n number of predictors. So out of n, for the first case, we will select any one. Okay. For the second case, we will select any two among the n number of predictors. And for the third case, we will select any three from the n number of predictors. Hope you will understand the story, what I am telling. Suppose, just a minute. Suppose I have 10 number of predictors. So for the first case, I will select only one number of predictors, any one number of predictors, any one. And for the second case, I will select only two number of predictors, any two. For the third case, I will select only three number of predictors, that is any three. So by carrying on this, suppose for the 20th cases, I will select 20 number of predictors, any 20. from out of 24 number of predictors. So that's why if you see for the first row, model selection tells us if we consider only one predictor, then the clay is the very important predictor. That's the message. Okay. So if we consider two predictors, then sand and I think, yes, sand and SP. These predictors are important if we consider only two number of predictors. So if we consider only three predictors, what are the best predictors? WSL, AT, and the clay. Okay, so see, for the first one, clay is there, but for the second one, clay is not there. Because if you consider only two number of predictors, then the importance of clay is not required. But if you consider three predictors, then the importance of clay is required. And you can see if we consider four, five, or six number of predictors, then sorry, four or five, then clay is there. But see, if we consider the six number of predictors or seven number of predictors or eight number of predictors, then it is not important to consider clay at all for predicting our data set. So that's the model selection. That means out of 24 number of predictors, which predictors are very much important. So that game is built by the model selection process or the best subset selection process. Okay. So, but the question is, up to what extent we will continue our experiment? That means how much number of predictors is suitable for us to predict or to draw inferences on our model selection process? That's a very important and a very significant question, because where I will stop. So that's why again I will show my next slide. Yes, that's the protocol that I have discussed here. Okay, that is the PK, that is the PCK. That means out of P, I will select the K number of vectors. So that I have already discussed through the summary thing. Okay. So that is the variance associated with the multiple linear regression. So now I will switch to my R studio. Yes. So what I have stopped, that is that up to what extent I will stop my process or I will stop my iterations. That's a very important question. Okay. So that means we have to use some extra statistical measure for drawing these inferences. And if you recall my talk in the first half of this talk, that I have mentioned that might not possible to partition the dataset into train and test always. But if we consider the whole dataset as a train data, then how can we predict the test data so that it will perform a good regression? Okay. So that's why we need extra statistical measure for predicting the optimal number of model selection cases. Okay. So in that case, I will show you in my next couple of slides, that is what is the very important extra measures are there. That is I am going to use one important statistical measure, that is the Bayesian information criterion, or the BIC. Okay. How can we get the BIC? Let me show you. Suppose I am storing the information of BIC for the base subset selection or just subset selection. I will definitely share you the detail of that thing, but I will first perform this thing. This is very much important. Suppose summary based subset selection, then put the dollar symbol. Yes. See, the BIC information is there. I'm just executing this line and let's see what is coming. Yes. So see. So what is the information represented here? If we consider only one model parameter, the BIC is there. If we consider two model parameters, the BIC is there. And if we consider three model parameters, then BIC is there. But why this BIC is very much important, or why this model parameter is again very much important? So again, I will show this by this slide. So as I have mentioned, that is the variance associated with the multiple linear regression. You have seen that couple of large variances is there. So what is the expectation of after the model selection? That it is expected that the variance associated with the model parameters will be reduced with respect to this one. Okay. So by the same fashion, we will execute the variance will execute or will extract the variance associated with the model parameters. Okay. So suppose, so let me write this thing. Okay. So suppose I am extracting the variance information of the best subset selection for one predictor consideration. Okay. Acha, okay. Oh, acha. Diagonal is required. Always diagonal is required because in the variance covariance matrix, the diagonal are representing by the variance, are represent variance. Okay. So by this thing, you will evaluate the variance of associated with the model parameters. I will tell you the underlying story, but I will first show you this one because unless you will not able to perform the variances. So again, yes. So suppose I want, if we consider 5 number of predictors. So see, for the 5 number predictor, the variance is associated. Now I am switching to my presentation file to display the underlying mechanism. Yes, as I have show you that if we consider one predictors, so what is the variance associated with the intercept? 0.47. See, when we perform the multiple linear regression by considering all the predictors, what is the variations? 10 to the power 5. But what is the variance right now by considering only one predictors? That is 0.47. So you can easily understand what is the utility of the model selection. That is, it has reduced the variance of the intercept too much. Okay. Similarly, the variance associated with the clay, see, 70 point something, the variance is there for the multiple linear regressions. And see, if we consider only one predictor, what is the variance associated with that? 0.007. That is too much low. That is for the one predictor case. But if we consider 5 predictors, see again, for the 5 predictors, with respect to one predictor, the variance has increased, but with respect to the multiple linear regression, see the variance is reduced again too much for the intercept cases. Always compare the variance of the predictors with respect to the multiple linear regression. That will be easy to you for the understand. And see for the AT cases, see for the AT, what is the variance? The variance is 0.006 and here also the variance is 0.008. Okay. And for the, again, for the SP cases, the variance is 0014. And for the clay, see the clay. So what is the variance associated with the clay? 0.004. Okay. And the variance associated with the clay here, 0.007. So instead of considering only one predictor, if we consider the 5 predictors, the variance associated with the clay parameters is reduced. Okay. The variance associated is reduced. So these boxes are placed with respect to this specific table. So see, if we consider 10 number of predictors, so see the variance of the intercept is increased very much. It becomes 30 point something. And see, for the AT cases, the variance has been increased because it is now 0.01. Here the variance is 0.008. And similarly for the SP cases, see, for the SP, the variance was 0.0001. But here, the variance is 0.000 but 3. Here, after 0001 is there, but here the after 000 3 is there. That means variance has been increased a little bit. But what is the expectation? If we increase our number of predictors, the variance must be reduced. That is the expected predictions or expectation from us. That means there remains certain optimality in between the 5 and 10 number of predictors. But how can we select or how can we choose the optimal number of predictors? So that's my next slide. That means the optimal model selection. And what is the optimal number of model parameters? Okay. So as I have mentioned, that can be done through the prediction or the estimation of the test error. So that can be performed in 2 ways: by adjusting the training error. That means if we consider the whole data set as the training data set, then we will receive the training error with respect to the whole data set, then we can adjust the training error. And again, we can directly estimate the test error. So, but here I will concentrate only for the first portion, because this requires another 1.5 hour for direct estimation of the test error. Okay. So by adjusting the training error, it generally contains three important statistical measures: the Manos CP, Akaike Information Criterion, that is AIC, and the Bayesian Information Criterion, the BIC. RSS means residual sum of squares, P means number of predictors, and sigma hat is nothing but the irreducible error. That means the error or the noise associated with the sample. But I will concentrate, or I will use only the BIC that I have displayed already. So what is the protocol of using the BIC, or what is the protocol of using this specific measure? That is, lower the value, better will be the model. So that means we will select, or we will look upon the parameters, or we will look upon the values for which the BIC is very low, or the AIC is very low, or the Manos CP is very low. So I am switching to the R Studio. So you can see I have already extracted the information on the BIC. Now I will see which is the minimum. Okay. So suppose I am storing my information at dot mean. So which is the minimum among the BIC? So BIC dot, sorry, subset dot selection. Yes. So what is the position? Let's see. Yes. So see, that means the seventh position of the BIC is low. Seventh position of the BIC is low. So as I have mentioned, all the positions are nothing but the consideration of the model parameters. That means first position is due to the consideration of the one predictor, second position is due to the consideration of the two predictors, and the third position is due to the third three predictors. That means the seventh position is the optimal. That means if we consider only 7 model parameters, so that is relevant for us, and that will produce a good output with respect to our data set. Now, generally, so that is the recent trend, or the better trend, to display all the information visually. So that is very much important. So how can we display this thing through graphical structure? So in that case, just I will plot the BIC dot subset selection. Suppose I am giving the color equal to dark blue, so that all of you can easily see that. And suppose type equal to O, that means both point and will be displayed. Line will be equal to, suppose I'm selecting 3, and X label, as I have mentioned, that in the X-axis, the number of predictors will be there. Okay. And then, sorry, and then in the Y-axis, Y lab, the BIC will be there. And suppose I'm increasing the font of the X-axis and Y-axis label by 1.3. Okay. So let us execute. See. So you can see the structure of the BIC, or the trend of the BIC. So if we consider the model parameters 1, 2, 3, see, when we increase the model parameters, the number of predictors, initially the BIC is decreasing, but after a certain threshold, it has been increased. And as I mentioned, the protocol that lower the value of the BIC, better will be the model. So what is the number of predictor for which the BIC is showing to be lowest? That is the 7th position. So suppose I am going to place this in the graph. So that is for which the comment will be points. And in that case, just I am writing that post dot mean, and again I am searching for the minimum position inside the PIC cases. Okay. So just placing that color equal to, suppose red, point character equal to 19. Yes. So acha, okay. So I will increase the size little bit so that it will be easy to use. Yes. So hope you can display this red ball here. So that is the graphical visualization by which you can display that the 7th position is showing the lowest one. Okay. So if we compare the variance of associated with the model parameters in case of the by consideration of 7 number of predictors, what will be the output? So let's see. Yes. So that is the variance associated with the multiple linear regression. Yes. So if we consider the 7 number of predictors, so this is the variance associated with the 7 number of predictors. So let's compare with the 10 number of predictors. See. So for the intercept case, see. So for the intercept case, the variance is 20. But for the 10 number of predictors, the variance is 30. So if we increase the model parameters, it is not good. So again, for the 80 cases, so here 80 cases, the variance associated with the model parameters is 0.010, but here 0.011. So that is little bit high. So that is also a very good symbol that with the help of low number of predictors, we are producing low variances. And similarly for the SP cases, see, for the SP cases, it is 10 to the power minus 4, it is also 10 to the power minus 4, but after decimal point, 3 decimal point, only 1 is there, but here 3 is there. So by incorporating the predictors, the variance is again high, but here the variance is low. So that is the point, or that's the conclusion I have to pass on to you, that it is not good to consider each and every all the predictors in the model. So that's why the tool of model selection came into the picture. Okay. But the portion or the picture that I have displayed here, or that summary that I have displayed here, how can we visualize this thing through graphical structure? Because it is always needed to display the information to by the graphical structure so that all of you can easily understand. Okay, so that's why I will plot the BIC for this specific model selection process. Okay. Yes. So see. So this is a very important picture. Okay. So I will show you by the slides so it will be very easy to use. Yes. So you can see the graphical demonstration of the best subset selection process. So generally what is happening, what generally I have seen by when I am reviewing the research article, I have seen that the researchers are producing the entire information based on a table. But it is very cumbersome to see all the information through the table structure. But if we see this entire structure through some graphs, then it will be easy for each and everyone to understand. So that's why the graphical visualization matters, and graphical visualization is very much important for each and everyone. Okay. So what I have mentioned, what is the protocol? The protocol is lower the value, better will be the model. So see, so if we go upwards, the BIC value stands to be low, and the highest low value may be minus 42. And now how can we select the model from the graphs? So go to the horizontal line. Okay, so see. So here intercept is always there. So the black box associated at the top horizontal line will be the key point or the key variables. Okay. So see, the intercept is there. So in the output, intercept is there. Acha. So see, DO is there at the top. So output DO is there. Acha. P new is there at the top. So P new is also there. And see, AT, sand, slit are there. So AT, sand, slit are there. SP is there. So SP is there. Acha. Then STN is there. Also STN is there. So hope you have understand what message I am trying to pass on to you. That is the information that you will give to your presentation or to your boss through just by tabulated structure. You can also give the information through this wonderful graph, so that this graph is also attracting and it will attract businessmen to see or to understand from the layman's perspective. Okay, so that is very much important information. Yes. So apart from that, apart from actually best subset selection, to another method is there, stepwise forward selection method, and second one stepwise backward selection method. Okay, so I have already taken, as I have seen, already 1.5 hours. Okay, so it is very, I am not going to explain this thing. If Somrit will give me another opportunity for another session in next couple of days or any next days, then I will explain this thing. Okay, the R code is very simple. Just we have to, just I am just showing to you that you have to write the same command. The command is same, rake subsets. The no new command is there for the base forward selection regression method or the forward backward regression method command is same. Just after this command, you have to just specify the method, nothing else. Method equal to forward. Okay. Then it will give you the forward regression information. But if you just type here backward, then it will provide the backward information, nothing else. And you have to perform the same thing. That is the BIC cases or the summary or the star. That means what is the number of optimal predictors for the forward selection cases and what is the number of optimal parameters for the backward regression cases. These are the codes are same. Okay. So hope all of you can understand what the message I am wishing to pass on to you through this talk. And as I have mentioned, that this demonstration could be happen through the specific library function libs, and the important command is rec subsets. So what is the take home message? We should select the models with less number of predictors. That means the large number of model parameters, selection of large number of model parameters is not good. As you have seen, the train and test MAC differs a lot. So that's why we have to select a very less amount of predictors so that it will produce a very good inference with respect to our model structure. Okay, and this is the reference book, and this is very much interesting and important book because this is written so nicely that any person who is not at all from the statistics background or the mathematics background, he or she can easily understand the essence of this specific machine learning or the underlying data science. That's why I have pasted this front page in these slides. Okay, with this, I am concluding my talk, and obviously, thanks for tolerating 1.5 hour. Thanks for tolerating myself. Okay, this 1.5 hour. So I have ended my presentation. So if you have any questions right now, you can easily ask me.
Yeah, thank you, Dr. Ayan Pal, for your wonderful presentation. So if you guys have any question, you can ask in the chat section, or you can unmute yourself to directly ask the speaker.
I think no questions is
I
there.
think no question. So yeah,
Yes.
thank you once again for your wonderful session.
Thank you very much for
And
you for giving the opportunity.
yeah, definitely. So we are the R user group. We usually organize this kind of sessions bi-monthly. So any one of you want to speak at this R user group, so you can reach out to us by email us at kolkatauser@gmail.com, or directly ask or directly message me in the WhatsApp or LinkedIn, whatever. All the platforms we are available. So thank you for this, and we are extending our heartfelt thanks to our sponsors, our consortium. Their commitment to our community has been instrumental in helping us to establish this group in my hometown, Kolkata. So we regularly follow their works, their contributions on LinkedIn blogs and their website, and we are proud to be part of this global art community. So that's it. We are wrapping up this session, and we will be come back again in the next month with another new sessions with another new topic. So thank you everyone. Goodbye.
Thank you very much. Thank you very much.
Yeah.
Okay. So I'm leaving the meeting. Okay.
Yeah.